Okay, so the second molecule that we're going to look at. So we just looked at a molecule that is linear with 2 bonding sites and no lone pairs. And the next one we're going to look at is also linear, but this time the central atom has 1 bonding site and 1 set of lone pairs. Hey guys, make sure you have goggles on before you're doing any tests over there. I see quite a few people without goggles on. Okay, this is an example of N2. So we have 1 bonding site that happens to be a triple bond, 1 bonding site, and then there's a set of lone pairs, whoops, on either of these molecules, or either of these atoms. So really there's no central atom here. In essence, there are 2 central atoms, but each atom has 1 lone pair, and this is still linear. Okay, so I'm going to go ahead and pass this one around. Okay, the next one that we talked about was trigonal planar, so we've already drawn that one, and I have a molecule built for you right here. Okay, now, what I want you to notice is, first of all, we have 3 bonding sites, and in this particular example, all 3 of those bonding sites are bonded. So, all 3 of these are bonded. This is trigonal planar. Notice that this is all in the same plane. This would be a 2D molecule. It's all in the same plane. Now, if we wanted to create a bent version of this molecule where we had 2 bonding sites and 1 lone pair, I'm just going to take this one off, and now we have a bent molecule. So now we have 2 sites that are bonded and 1 site that has a lone pair. Now, the other one that we drew that I actually don't have shown on here, but if we had 3 bonding sites, but only 1 was bonded and 2 were lone pairs, we would have a linear structure. Do you follow me so far? Okay, so I'm going to put these back on. Let's talk a little bit about bond angles. The bond angle from here to here, whoops, bond angle from here to here is 120 degrees. If I take this off and we have a bent molecule, you can't really show it with this particular molecule, but the lone pair up here pushes these 2 atoms closer together, so the bond angle would be less than 120 degrees. Now, I think yesterday we wrote 104.5 degrees, but actually that is the angle when you have a bent molecule with 2 lone pairs. So the actual bond angle here is not important. The only thing that's important is that you know that it's less than 120 degrees because the lone pair is exhibiting more of a electronegative force on the bonded pairs. And then, if we have 2 lone pairs and 1 bonded pair, then we have a 180 degree bond angle. Alright, so I'm going to put these back on and pass this around. Okay, the next structure, which we haven't drawn yet, is when we have 4 electron density sites of electron density. So over here, it says bonded pairs. I'm actually going to cross this off. Bonded pairs. I'm going to write sites of electron density. And that's the same for all of those. All of these should be sites of electron density. So if we have 4 sites of electron density, and all 4 of those sites are bonded, we get a tetrahedral structure. I'm going to do my best to draw this. Okay, so I tried to draw a dotted line there, it didn't really work out, but that one is going back into the plane of the page. So, here's your 3D structure. Okay, this is tetrahedral. The bond angle between each of these terminal atoms is 109.5 degrees. I'm going to write that right here. 109.5 degrees. The geometry is tetrahedral. And then the type would be MX4. Okay, now, if we remove one of these, we get our next structure, which is called trigonal pyramidal. So you can see this is still a 2D structure. And I'm going to try and draw a trigonal pyramidal here. Okay, there's trigonal pyramidal. Let me make those dots a little bit bigger. So we have our lone pairs up top. The bond angle for trigonal pyramidal is 107 degrees. And again, the geometry is trigonal pyramidal. And then the type would be MX3E.
What is that bond angle? 107?
107, yes. Okay, now, if we take two of these off, then we get a bent molecule. Okay, so here's our bent molecule. The bond angle here is 104.5 degrees. So again, the more lone pairs that we add, the closer we are pushing these two bonded pairs together. The geometry here is bent, and the type is MX2E2. And I'm not actually going to draw this one, but if we did remove this last one here and we had one shared pair and three lone pairs, it would be a linear structure, 180 degrees. An example of this would be like hydrochloric acid, HCl, where Cl would have three lone pairs and then one bonded pair to hydrogen. Okay, so I'm going to put this back together. Feel free when I'm passing these around to pull them apart, observe the bond angles, especially with these next two. All right, here's tetrahedron. All right, this next one, when we have 5 bonded pairs, bring that here. This is called trigonal bipyramidal. And I'm going to do my absolute best to draw this, and it's not going to look all that amazing, so prepare yourself. Okay. So we have our central atom here, and then let's try it this way. Three like that, and then one would be going into the plane of the board, so a dotted line, and then one would be coming out of the plane like that. Okay, something like that. But this is what it actually looks like. Okay, so the bond angle here, we actually have multiple bond angles. We have 90-degree bond angles and 120-degree bond angles. So, when we take a look at the structure, the angles here and here are 90-degree bond angles. And you can actually see that. That looks like a 90-degree bond angle. But, let's see if I can, the bond angles here and here and here are 120 degree bond angles. So there are 2 90 degree bond angles and 3 120 degree bond angles. Okay, now, if we remove one of these, the structure that we get is called a seesaw structure. The reason they call it seesaw is because it kind of looks like a seesaw. This would be like the fulcrum, and these would be the seats of the seesaw. This is called a seesaw structure. So this is if we have 4 bonded pairs and 1 lone pair. I'm going to set this to the side and finish filling in this information here. Again, this is trigonal bipyramid, right? Yeah, trigonal bipyramidal. And the type here would be MX5. Okay, but this next one, we have our central atom, and then a lone pair, so something like that. Again, I apologize if that's difficult to see. The resolution has to be low in order for me to be able to record. Okay, so this is a seesaw structure. The bond angle on a seesaw structure, we actually have 3 different bond angles here. We have 90 degree bond angles. We have 120 degree bond angles. And we have 180 degree bond angles. So let's take a look at this. Those 90 degree bond angles are going to be here and here. So this is 90 degrees, this is 90 degrees. So we have 2 90 degree bond angles. All right. Here we have a 120 degree bond angle. It's kind of difficult to see, but right there, 120 degree bond angle. So we have 1 120 degree bond angle. And then here, we have 1 180 degree bond angle. All right. So this is called a seesaw. And the type would be MX4E. Okay, let's remove another. Oops, if I can get it off. There we go. Okay. This is called a T-shaped structure for obvious reasons. It looks like a T. So, T-shaped structure, we're going to have our central atom, 2 sets of lone pairs, and we have 2 different bond angles here, 90 degree bond angles and 180 degree bond angles. We have 2 90 degree bond angles and 1 180 degree bond angle. So you can see the 90 degrees bond angles are right here and right here, and the 180 degree bond angle is right here.
Why does the valent or the electron pairs not push the other, like why does it not bend them?
Great question. So why are these not as bent as some of the other molecules that we've seen? Well, we have 2 lone pairs, it's true, but now we also have more bonded atoms. And those bonded atoms are also exhibiting electron-electron repulsion. So when we only had 1 lone pair, and two bonded atoms, like for example, with the bent structure here, we had one lone pair and two bonded atoms. The two bonded atoms are exhibiting an electron-electron repulsion force on each other, but the repulsion force of the lone pair is greater, so it pushes those closer together. Here, we have three bonded pairs. So even though these two lone pairs are exhibiting a great amount of repulsive force, these three pairs are also exhibiting a great amount of repulsive force against each other. So this is the structure we end up with, a T-shaped structure. Okay, the geometry here is T-shaped. And the type would be MX3E2. Okay. If we lose another one, we get a linear structure. Bond angle here is 180 degrees, geometry is linear, and the type is MX2E3. Now, it seems to be that the greatest number of lone pairs we can have around a central atom are 3 lone pairs. We haven't yet seen a central atom that has 4 lone pairs surrounding it. It's just too much repulsion. So the greatest number of lone pairs we can see around a central atom is 3 sets of lone pairs. We never see 4. So this is the last structure. I'm going to go ahead and put this one back together, pass it around. Again, feel free to take it apart to see the different bond angles and the different structures. All right, the last one, octahedral. We have 6 electron density sites. And this is the shape that we get. All right, so I'm going to give drawing this a try. All right, so we have our central atom here, then bonded pair here, here. Okay, so not the best drawing, but these two are going back into the paper and these two are coming out of the paper. The bond angle here is all 90-degree angles. The geometry is called octahedral, and the type is MX6. Okay, so this is actually pretty easy to see all of the different bond angles. So here we have a 90-degree bond angle. Here we have a 90-degree bond angle. We turn it this way. This is a 90-degree bond angle. This is a 90-degree bond angle. So all of the bond angles are 90 degrees. All right. If we remove one, we get a structure that is called square pyramidal. And this is why they call it square pyramidal, because if you picture it as a 3D molecule, it kind of looks like a pyramid with a base that is a square. So this is called square pyramidal. All right, I'll draw out this. Okay. The bond angles here are 90-degree bond angles and 180-degree bond angles. Most of the bond angles are 90-degree bond angles. We have 1, 2, 3, 4, 5, 6, 7, 8 90-degree bond angles. But here we have 2 180-degree bond angles. You don't actually need to know the total number of bond angles, but it does help to picture it. Okay. I'm sorry, this is called square pyramidal. And the type is MX5E1. Okay, if we remove another, we get this structure, which is called square planar. Again, it's called square planar because now if you look, all of these atoms are in the same plane. So this would look like this. Or something like this. Okay. The bond angles here are again 90-degree bond angles and 180-degree bond angles. These bond angles here are all 90-degree bond angles, but flip it on its side here. This is a 180-degree bond angle. And this is a 180-degree bond angle. The geometry is called square planar. And the type is MX4E2. Okay. If we remove another one, we get T-shaped again. So this will look like this. And if you can't see those lone pairs, I've got 2 right here, 2 here, and 2 there. Okay. Bond angles here, again, 90 degrees and 180 degrees. This is T-shaped. So we've got 90-degree bond angles here and here, but 180-degree bond angle here. Finally, oops. Oh, I'm sorry, this is MX3E3. Now, this last one that I'm going to show you doesn't really happen because I've already said that we really don't get 4 sets of lone pairs around a central atom. But I'm going to show you the structure anyway, just so you're familiar with it. What happens here, and again, this doesn't actually ever happen, is we get 4 sets of lone pairs around the central atom, and the structure is linear with a 180-degree bond angle, and the bond type would be MX2E4. Okay, I'm going to go ahead and put this back together and pass that around. And I'm going to stop this video.